Today, we will learn about deep computer vision. This lecture is designed to give you both conceptual intuition and practical grounding in how modern vision systems work, particularly in medicine and global health. Computer vision aims to replicate what humans do effortlessly in our visual apparatus. This is transforming photons perceived by the eye's retina into meaningful decisions, all computed within the brain. While this may feel trivial in daily life, as it happens in the optic circuitry and brain of every physician working in global health, emulating such a process through engineering is both non-trivial and remarkably complex, especially if you consider that in healthcare, decisions must be remarkably accurate, explainable, and robust. Deep computer vision already plays a transformative role across medicine and biology, such as in radiology, pathology, dermatology, ophthalmology, and infectious disease surveillance. In global health settings, these tools are especially powerful because they can extend expert-level analysis to resource-limited environments. Across modalities, X-ray, ultrasound, CT, MRI, OCT, or microscopy, the unifying abstraction is the same. Images presented as matrices of numbers. Different phi-6, same computational representation. Once an image is acquired, we may want to classify it, such as disease versus no disease, regress a value such as a severity score, detect objects, are there lesions or not, and if so, what are they? Segment regions, for example, delineate the borders or surfaces of organs, vessels, or tumors. These tasks form the backbone of medical AI applications. Every computer vision system follows a familiar sequence. First, image acquisition or input, numerical encoding or conversion into a compatible representation, typically a matrix of integers with values ranging from 0 to 255 in grayscale, or as 3D vectors in RGB. After this, such a universal pipeline can include value preprocessing, such as normalization. Then, the data is split to perform model training. Once a model is trained, it can be used for pattern identification, feature extraction, or other downstream tasks, which are then used for evaluation and iterative system refinement. Digitally, images can be encoded as tensors. As such, a color image is typically represented as a matrix of size, height, times width, times channels, where each matrix element stores intensity values, often in 0 to 255, due to 8-bit encoding. Alternative normalizations, such as scaling in the 0 to 1 range as floating point numbers, are also common in deep learning. As a side note, the pre-processing of such matrix representations of images can include mathematical operations in vector space, such as normalization, binarization, and contrast adjustment. This pre-processing can be really important and determine whether a specific model architecture will converge and learn meaningful image representations or just spurious artifacts, especially in heterogeneous clinical datasets. Overall, though, the point of this matrix representation of images that will be to use them as input for deep learning models, themselves based on the neural network building blocks that will attempt to learn functions that robustly transform such inputs into classification prediction probabilities, or to regress continuous variables. Here you can see this general concept on a CAD image, but you can expand this concept to anything visual, such as radiographs or photographs of clinical issues. To understand the fundamentals of computer vision, one has to recognize that all objects around us are inherently hierarchical. Houses are made of windows, walls, doors, and roofs, while faces are composed of eyes, noses, mouths, ears, and foreheads. And the car has wheels, doors, windshields, and a chassis. However, one can also ask oneself, for example, when does a car stop being a car? What happens if that vehicle on the right has only 3 wheels? Is that still a car? What happens if there are only 2 wheels? Is a face still a face if it is missing an eye or 2? Such questions may appear borderline ridiculous, no more than a mere ontological game. But this discussion is at the core of what computer vision aims to understand fundamentally and to replicate, as useful vision models must learn and generalize meaningful hierarchies of the visual world, in a way that is robust and capable of solving interesting tasks in the real world. Turns out, one way to think about these hierarchical representations is in terms of so-called low-level, medium-level, and high-level visual features. Low-level features may be things like blobs and edges, which constitute very simple and fairly indivisible visual archetypes. Medium-level features may be simple combinations of a few low-level features. Interestingly, some familiar face archetypes, in low resolution, can be considered medium-level features, such as the eyes, eyebrows, and noses you see in the middle panel. Finally, Higher level features are themselves combinations of multiple medium level features. The classes of neural network systems that we will evaluate in this course will, to our surprise, find a way to learn filters or pattern recognition functions to detect low, medium, and high level features in the input image that are relevant for the final prediction task. Typically, it's with early layers of these neural networks for detecting edges and blobs. Intermediate layers assemble these into motifs like eyes or wheels. Deeper layers encode semantic concepts such as faces, cars, or disease patterns. Dealing with real-world images means there needs to be ways to account for viewpoint variation, deformations, occlusions, changes in illumination, and background clutter. Robust computer vision systems must handle all of these simultaneously. Okay, so how do we train a system to recognize meaningful visual features for our tasks? Well, of course, we can start with a fully connected neural network with n hidden layers, and we can set this network to accept every single value of the input image canvas as input. This may look like a good idea, but this would likely entail flattening every input image into a linear vector, which could destroy spatial structure, or at least make it more challenging to learn. Additionally, treating the input in this way leads to an explosion in parameters as we want to accept larger and larger images, which are very common nowadays in everyday use, with megapixel-sized images commonplace in everyday life and clinical interactions. Both the parameter explosion problem and the make learning inefficient and brittle. A fascinating insight into more robust computer vision emerged when considering adding priors to the vision task, and the fact that the spatial relationships among neighboring pixels are particularly important. In this way, the convolution function emerged as a great option to preserve spatial locality, while dramatically reducing parameter count. In a convolutional neural network, every neuron processes a local receptive field rather than the entire image. The convolution operation applies a small kernel across an image, computing weighted sums of local neighborhoods. Mathematically, this is a linear operation rooted in signal processing for radio and telecommunications, as well as wired lines. Convolution is a mathematical operation that describes how one signal influences another over time or space. You can think of it as taking an input signal and passing it through a system characterized by its impulse response. To compute the output, we flip the impulse response, slide it across the input, and at each position multiply the overlapping values and sum them. This process captures how past values of the input contribute to the current output, weighted by how strongly the system responds after a delay. Whether written as an integral in continuous time or a sum in discrete time, convolution formalizes the idea that an output signal is the accumulated time-shifted, or in this case, pixel-shifted effect of the input. Here, the convolution operation is shown in its concrete, image-based form using a kernel or filter. Let us consider an arbitrary small image and small kernel to help us visualize what is going on. We start with a 6x6 input image and a 3x3 kernel. The kernel is placed over a local 3x3 patch of the image, where corresponding values are multiplied element by element, and then summed to produce a single output value. That value becomes one cell in the output feature map. The kernel then slides across the image, repeating this process at every valid position. Each output pixel, therefore, summarizes a local region of the input, capturing specific patterns, such as edges, gradients, or textures depending on the kernel's values. This sliding multiply and sum operation is the core mechanism by which convolutional neural networks extract meaningful spatial features in images. One interesting result of this is that each kernel responds maximally to specific patterns, edges, textures, or blobs, which can be used to robustly detect higher-level objects, coordinating detection, or more invariant mid-level and lower-level features. During the training of a convolutional neural network, learning these kernels automatically via backpropagation will be our fundamental goal. Here you can see the three fundamental kernels needed to robustly detect a low-resolution X, even if not perfect, slightly rotated, or kinked. A second example exemplifies, in a more graphical way, the effect of an eye kernel convolution over a face, which produces maximum activation in the regions where the two eyes are present. Applying multiple filters this way produces feature maps, which are new image representations that emphasize different visual patterns. These can be used as a basis for the detection of patterns within our neural networks, but can also be used as pre-processing stages to sharpen an image, detect edges, or even remove noise. Alright, let us now do a deep dive into convolutional neural networks, also known as CNNs. Here you can see how convolution is used end-to-end in a convolutional neural network for image classification of common pathologies in chest X-rays, a typical computer vision application in global health. The input image is processed by multiple convolutional layers, where learned kernels slide over the image to produce feature maps that detect increasingly complex patterns. After each convolution, a nonlinear activation such as ReLU is applied. ReLU is an expressive choice for a nonlinear activation function, necessary for most neural networks, that also has the property of suppressing negative responses and preserving positive ones, which is a necessary condition for producing valid image pixel outputs. Convolutions and ReLU activations are then followed by pooling layers that reduce spatial resolution while preserving the information that is most important. Essentially, pulling down samples and the feature maps, reducing dimensionality, improving generalization, and increasing robustness to small spatial shifts. This sequence of convolution, activation, and pooling forms the feature extraction layer of every CNN and enables these neural networks to learn increasingly abstract representations. Here, you can see again the kernel panels we initially showed, which hopefully will surprise you to know that these kernels or convolutional layers were learned, rather than heuristically determined. At least to me, it feels quite remarkable that such realistic-looking filters emerge from such a training process. Therefore, the algorithm is as follows: image input, convolution, ReLU, pooling, repeat, convolution, ReLU, pooling, repeat, convolution, ReLU, pooling, repeat, and so on. The resulting feature maps are then flattened and passed into fully connected layers, which combine the extracted features to make a final decision. A softmax activation at the output works by converting these scores into class probabilities, yielding a probabilistic prediction over possible categories, which is a typical output choice for classification tasks. This diagram here shows more details on this convolutional neural network architecture, adapted for chess X-ray analysis, assuming 10 arbitrary possible pathological outcomes to expand on this concept. The input is a 28 by 28 grayscale image, which is first processed by a convolutional layer with 32 filters of size, 3 by 3, stride 1, and padding 1, followed by a ReLU activation, producing 32 feature maps of size 28 by 28. A 2 by 2 max pooling layer with stride 2 reduces the spatial resolution to 32 by 14 by 14. A second convolutional layer with 64 filters, again using 3 by 3 kernels with stride 1 and padding 1, and followed by ReLU, extracts higher level anatomical and pathological features, resulting in 64 by 14 by 14 feature maps. Another 2 by 2 max pooling layer downsamples these to 64 by 7 by 7. The feature maps are then flattened into a 3136 dimensional vector and passed to a fully connected layer with 128 units that integrates the learned features. The final output layer consists of 10 neurons, each corresponding to a different possible chest X-ray pathology, producing scores that are typically converted into class probabilities using softmax to support multi-class or multi-label clinical assessment. CNNs of this kind are trained exactly like other neural networks, which we have seen in great detail in previous lectures. Essentially, we perform 1. A forward pass, 2. Loss computation, 3. Gradient descent, 4. Backpropagation of gradients, and 5. Weight updates, again and again over many epochs, until the network has learned sufficiently to perform adequately on a holdout test set. Although the use of convolution in neural networks now date back decades, it cannot be overstated how important was the field Chan since the release of 2012 AlexNet, which demonstrated the power of deep CNNs at scale. The modern deep computer vision systems can predict multiple outputs simultaneously: classification, localization, and regression using shared feature representations, which are topics we will cover in future lectures, including object detection models like You Only Look Once, or YOLO, and segmentation networks enable real-time diagnostics, screening, and disease monitoring in low-resource settings. CNNs remain foundational, even as vision transformers have emerged as the more common computer vision architectures today. Thus, understanding convolution and CNNs is essential before moving on to other topics in this series of lectures. Before we conclude this lecture, I want to show you something very cool: a visual evolution of common deep computer vision architectures for handwritten digit recognition, a canonical vision task, to give you a more visceral, intuitive sense of the types of systems we are dealing with when talking about CNNs. First, see here a single perceptron model trained on this kind of data. Then, you can see an analogous multi-layer perceptron model, showing this layered abstraction with a hierarchical response that feels visually messy and not very structured. This can be contrasted to the operation of convolutional neural networks, which immediately look more hierarchical and structured in a more human interpretable way. This demo by Denis Dmitriev finalizes with a sample of a spiking network, which is yet another architecture that attempts to emulate the spiking behavior of real neurons in biological brains, evincing other interesting patterns and structures. Remember, deep computer vision is not about memorizing architectures, but about understanding how spatial information is encoded, transformed, and used for decision making. Great! This concludes our introductory lecture on deep computer vision with a focus on convolutional neural networks. In future lectures, we will learn more about vision transformers and compare them with CNNs, building on today's foundations. Thank you for tuning in, and see you next time.